Okay, so when we're passing parameters to a subroutine, we can either put those parameters in registers, and then obviously in the subroutine, we use those registers, the parameters that are in those registers. Or if we have lots of stuff to pass to a subroutine, we can put that stuff, that data, on the stack, okay? Other things we use the stack for when we call a subroutine is to save the return address for the end of the subroutine when we go back to the code that called the subroutine. If we have nested subroutines where we call a subroutine and then within that subroutine we call yet another subroutine, well, we have to save the return address for the first subroutine somewhere as well, because that register that holds that return address, called the link register, will get overwritten when we call the second subroutine. So we have to store that return address for the first subroutine somewhere. We store it on the stack typically, okay? And then we can also make room on the stack for what we call local variables. So we might need some memory locations to store intermediate values in when we do some calculations within a subroutine, so we can make room on the stack for those as well. So those are some of the uses of the stack when we are calling subroutines. So we just started, I think, this subroutine example last day, so let's work our way through it. It's again, the application here is adding up a list of numbers. Okay, so we'll draw our subroutine, or pardon me, our stack over here to keep track of what's in it. Okay, so when this bit of code runs, we can assume maybe that our top of stack here is here. So, and the top of the stack is just our stack pointer, which in the ARM is R13. Okay, so register R13 is the stack pointer in ARM. And again, the stack pointer holds an address. It's a pointer, so it holds an address. So when this code runs, we're going to assume that it's holding the address for this memory location. It doesn't hold what's in here. It holds the address of this location in memory, whatever that address is. And presumably there's some important piece of data in that being stored in that memory location. Okay, so up here in our calling program, first thing we're going to do is we're going to push the parameters that we need in our subroutine onto the stack. So first instruction is going to load register R0 with the address num1. Okay, so this is num1 is a label for some address in memory, and we're going to load that address into R0. And then we're going to store we're going to store what's in R0, which is this address num1, on the stack. Okay, the square brackets means the indexed form of addressing. There's an offset, an immediate offset inside, so this is the pre-indexed addressing mode, which means the effective address in memory where we are going to store the contents of R0 is what's in R13, and R13 currently it holds the address of this memory location. So to that address we're going to add -4, which will be the address of this memory location, right? This is lower addresses, this is higher addresses. So we're going to take the address of this memory location, subtract 4 for it, so we now get the address for this memory location. That is the effective address for this instruction, this store instruction. Okay, so whatever's in R0 gets stored there. And what is currently in R0 is the address num1. So num1 is going to be stored there. Okay. And then because of this exclamation mark, we have write back, which means the register inside the square brackets is actually changed to its new value. Okay? So now R13, our stack pointer, is pointing here. It now contains the address of this memory location. And what's stored at that memory location is an address called num1. Okay, so we've pushed that onto the stack. Again, without this exclamation mark, the effective address would still be R13 -4. It would still be the address for this memory location. So the contents of R0, num1 would still be stored here, but then R13 would still be pointing here. Okay? But with this exclamation mark, R13 gets changed to this address. So it's pointing here now. Okay? So that's pre-indexed with write back. Now we're going to store push the next parameter on the stack. We're going to load register R0 with what is at address capital N. So N is somewhere else in memory, just like num1 is an address somewhere else in memory. So we're going to go to memory location N, whatever is stored there, which is the number of numbers in our list, small n, let's call it. That's going to be put into R0. And now we're going to store the contents of R0, small n, again at R13 minus 4. Okay, R13 is currently pointing here, so R13 minus 4 would be pointing here. And we're going to store small n there. And now R13 points here. R13 is our stack pointer, again, because we have write back here. Okay, so those first four instructions just push our two parameters onto the stack. In the previous example, we put those two parameters in registers. I forget which registers, R1 and R2 or something. And then we access those parameters in the subroutine just using R1 and R2. This time we're putting them on the stack. Okay, and then we are going to branch and link. BL means branch and link, so it's a branch instruction. Link means the processor will automatically save the return address of the next instruction, which would be this instruction here, in the link register, which is R14. Without the L, it'll still branch, but it won't save the return address in the link register. Okay, so when we call a subroutine, we want to branch and link. If you just want to branch somewhere else in your code and you never come back here, well then you can just use a B. But in this case, after we do the subroutine, we want to come back and do this, so we branch and link. So the return address is stored in L14. Okay, so somewhere we're going to have R14, which is our link register, and it's going to hold the address of, I don't know, I'm going to call it A1 here. It's going to hold address A1. The address of that instruction, LDR R0 R13, number 4. Okay, and then the processor will, also what happens with the branch instruction is the address of the first instruction in our subroutine, which is the address list add, would be placed in the program counter, which is R15. And the program counter is a register that tells the processor, where's the next instruction that I'm supposed to execute? Okay, so the branch instruction obviously needs to change the program counter, PC program counter, to this address, so that after doing this branch, it's going to do this address, this instruction next. Okay. Okay, so if we want our program counter, we could keep track of that too. Our program counter, which is R15, will have list add put into it, that address. Okay, so then we go to the subroutine, okay, because that's where the program counter tells us where to go next. So we go here. Now we're going to store some stuff on the stack. So this is a store, multiple, fully descending, means the address in R13 is going to be decrement. We're going to descend in addresses as we store the contents of these registers to where R13 is pointing. And R13 is our stack pointer, so we're going to put a bunch of stuff on the stack. We're going to put the contents of registers R0, R1, R2, R3, and R14. For this instruction, it's going to actually do it from the back, from right to left. So R14, which is our link register, its contents will be pushed onto the stack where R13 is going to be pointing. So it's going to pre-decrement R13, okay, because R13, our stack pointer, is always pointing to the top of our stack. Obviously, we don't want to write the contents of R14 over small n, so it's going to decrement by one memory word what's in R13 first, and then it's going to store the contents of R14 there. R14 currently holds this address A1 I'm just going to call it, well, let's call it A1. Okay, that address. We're going to store the return address of where we're going back to. Okay, and then it's going to store the contents of R3 there. So contents of R3, we don't know what that is right now. Contents of R2 will be next, R1, and finally R0. Okay, and R13, because of this exclamation mark, we have write back, which means R13 gets changed every time, right? It gets changed to this, we write that address A1, gets changed to this, to this, to this, to this. Okay, it gets pre-decremented, so that means after we write the contents of R0 in there, R13 is going to be our stack pointer is pointing there. Always to the top of the stack, the last thing that we put on the stack. Okay, so we've saved a bunch of registers, presumably because we're going to use these registers in our subroutine, and therefore we don't want to overwrite and permanently lose whatever was in them, because maybe what was in them was important to our calling program, okay? Okay, and then we're going to load register R1 with what's with the address, the effective address, which is the contents of R13 plus 20. So R13 currently has the address of this memory location in it. Stack pointer is pointing here. 20 divided by 4 is 5. So R13 plus 5, 1, 2, 3, 4, 5. So this number of numbers, small n, is going to be loaded into R1. So I'm running out of space here. Let's put R1 down here. Okay, so R1 is going to get small n put in it. Now there is no exclamation mark here. This is the pre-index mode, but no exclamation mark means no write back, which means at the end of this instruction, R13 still has the address of this location in it. It hasn't been changed. Okay? Then we're going to load register R2 with what's in with the effective address of what's in R13 plus 24. 24 divided by 4 is 6, so R13 still is pointing here. 1, 2, 3, 4, 5, 6. So we're going to take this address and load it into register R2. Again, no write back, so R13 is still pointing at the top of the stack. So that address, num1, is now in register R2. Now we're going to move 0 into R0. It's just a way of clearing register R0. Because when we write or when we save the contents of R0 onto the stack here, that doesn't mean that the contents of R0 go away. R0 still has what it had in it before we save a copy of it on the stack. So we're going to use R0 as our running sum, so we've got to set it equal to 0. Okay, now we're going to load register R3 with what's in with what's at the address contained in R2. Okay, this is the post-index mode, addressing mode, because the immediate operand is outside. So it's going to take the address in R2, which is num1, okay, and it's going to take whatever is at address num1, which is the first number in our list of numbers, and it's going to put it into R3. R3, let's put R3 up here. First number, whatever it is. First number in our list gets put into R3, okay, and now, because it's post-indexed, it's always write back. Even though you don't need the exclamation mark, it's always write back because it's post-index. So now we add 4 to R2, so R2 becomes num1 plus 4. So R2 is now pointing to the second number in our list. Okay, num1 plus 4 is the address of the second number in our list. Now we're going to add the contents of R3 to R0 and put the result in R0. 0 plus first number is first number. First number. Okay. Now we have a subtract instruction. We're going to subtract the immediate operand from what's in R1, which is the number of numbers, and put the result back into R1. So R1 now holds n minus 1. Okay, and the S suffix means this instruction is also going to update the condition bits in the processor status register. Okay, without the S, it wouldn't. But any instruction in ARM can be made such as to update the status register by putting S at the end of it. A lot of the times we don't need it, okay? Certain instructions always change the status register, and those are the ones like TST, to test, or TEQ, test if equal, and CMP, compare. Those, you don't need the suffix S. They always update the status register. But for every other instruction, if you want that instruction to update the status register, you put an S at the end. Why would we want to do it here? Well, because we're going to use a branch of greater than 0 instruction right after it. And so what are we looking for here? We're looking for when our counter here gets down to 0. Okay? So that means we need this instruction, the subtract instruction, to update the status bit, particularly the Z, the 0 bit, so that when this gets down to 0, this Z bit's going to be set equal to 1 due to this S, the Z bit in the status register. And that means this branch now will go, this branch greater than looks at that Z bit to decide whether to branch or not. Okay? So the sub updates the Z bit based on what happened here in this subtraction. And if we got down to 0, the Z bit is going to be equal to 1, and the branch won't happen because branch GT means branch greater than 0. Okay, so when we hit 0, well, that's no longer true, so we're not going to branch back. But until this gets down to 0, this is going to keep branching back to here, and we're just going to keep looping through here, adding one number after another, and this counter is going to go down one at a time until it finally hits 0. Then this branch doesn't happen anymore, and so we go on to this instruction here. So at the end of this, R0 is going to, R0 is going to be equal to the, I'll just say, sum of numbers, okay? We come out of the loop, and now we're going to store the contents of R0 somewhere, because the next instruction is going to restore R0 to what its contents were when we came into the subroutine. So we better store our result somewhere, otherwise it's going to get overwritten by this instruction. Okay, so we're going to store the contents of R0 where? On the stack. This is the pre-indexed mode without write back. So that means your effective address is what is R13. R13 is pointing here, so R13 currently holds the address of this memory location. And we're going to add to that address 24. 24 divided by 4 is 6. So 1, 2, 3, 4, 5, 6. So our effective address is the address of this memory location. Okay? And what are we going to store there? What's in R0, which is the sum? So we're going to overwrite this, and we're going to put sum in there instead. Okay? We don't need num1 anymore because we're done adding up the numbers. So we overwrite that parameter with the result. You know, I could have also put it here. Okay, pardon me. I could have also put it here because I don't need this anymore either. This parameter. These are the two parameters we passed. We're at the end of the subroutine. We don't need them anymore. I could have overwritten either one of these with the result sum. I don't want to overwrite this one because I still need this one. I don't want to overwrite any of these because I still need these when I restore the registers. Okay, and then finally, before we go back, we're going to pop a bunch of stuff off of our stack. Okay, so this is load multiple, fully descending, even though R13 is going to go up now. It just corresponds to this store instruction up here. But this time it's going to pop things off in reverse order, right? Because a stack is last in, first out. The last in was R0, so that's the first one that comes out. So we still write them in ascending order in both cases, but in the store, they're treated right to left. In the load, they get treated left to right. So the first thing that comes off the stack, which is pointed to by R13, is this number, and it gets put into R0. Then R13 is incremented by 4. because of, and save, so now R13 is pointing here. And we take that value and put it into the next register, which is R1. Next one R2, next one R3, and then finally the last one, which is the return address. It's the address of the next instruction after the branch instruction in our calling program gets loaded into R15, which is our program counter, which tells the processor where's the next instruction I got to do after I finish this one. Okay, so by putting this address here into R15, pardon me, we're telling the processor where to go back after this instruction. We're going to go back up to here. Okay? Okay, now where is the stack pointer after this instruction is done? Well, it started here. Okay, when we're loading, it's going to just use that stack pointer to pop off the first thing on the top of our stack and put it in R0, and then it increments it to here, pops R1, increments it to here, pops R2, increments it to here, pops R3. Increments it to here, pops A1. Okay? So it pops, increments, pops. Is that what I said before? I don't think so. It pops and then increments, R13. Pops, then increments, pops, then increments, pops, then increments, pops, then increments. So after this load instruction is down here, my stack pointer is now back to pointing to here, the top of the stack. Okay? I've effectively removed these memory locations from my stack, so my top of stack is now here. After this instruction is done, okay, we go to what is in R15, which is the program counter, which is now here, points here, and so we're going to do this now, okay? It was the calling program that put these parameters on the stack, so typically we want the calling program to take those numbers off the stack, okay? Could have done it in here too. How would I have taken these two numbers here off of the stack inside my subroutine at the end here? What would I have had to have done? Well, it's a little difficult because by putting this address A1 into R15, what's the next instruction that's going to be executed? It's going to be this one up here, right, at address A1. So that means I'm not able to add another instruction down here to decrement the stack pointer by 2 memory words so that it's now pointing to back to here. Okay, it's currently right here. If I decremented by 2 or incremented by 2 memory words, it would now be pointing here, which is what I eventually want to do. But I can't do it here because this has to be the last instruction because I'm updating the program counter here. So that means I have to do it back here in my calling program once I get back here. Okay, so that after we get back here, we're going to load register R0 with the effective address of what's in R13 plus 4. R13 is currently this memory, the address of this memory location. Plus 4 is this one, so it's going to take sum here, and it's going to put it into, where am I here? It's going to put it into R0. So now R0 has sum in it. Do I have an R0? Oh, it still has sum in it. It had it in here. We're just making sure, load register R0 with what came off the stack, which is a sum, kind of redundant because R0 already had the sum in it. Then we're going to store R0 at some address sum. Okay, so somewhere else in memory here, there's a memory location with the address sum. And so this number that was in R0 is going to be put into here now. Okay, so we're storing the result somewhere in memory. And now, finally, we are going to update the stack because we don't need the top of the stack here anymore. We don't need these 2 locations on our stack anymore. So now we just add 8 to what's in R13, our stack pointer. So now the stack pointer is back down to here. Okay? That doesn't mean these 2 memory locations still don't include these numbers. They do. Okay? It's just we've changed the top of our stack to be here now. So these locations are no longer part of the stack. Any questions about that one?
I'm just curious, so we didn't really bother with a frame pointer for
No, because we only have one subroutine.
Yeah, okay.
Yeah.
So you usually only use frame pointers?
Usually-
Doing nested?
Usually you only use frame pointers in nested subroutines when, you know, you're putting, for one subroutine, you gotta put a bunch of stuff on the stack, and then for the next one, you gotta put a bunch on the stack. Now, technically, you really don't need the frame pointer. You could always use the stack pointer to access different things in the stack, but it's just a little more convenient. Good question, though. Okay, so, good segue to our last example. A little bit longer. This time we've got 2 subroutines that we're gonna call. Okay, so let's go through the same process. I'm not gonna go through the same excruciating detail about all the addressing modes. You guys should be starting to get familiar with those. But if anybody has a question, if you don't understand something and I don't explain it, please let me know, because it's important to understand all this stuff. And we'll do the same thing. We'll keep track of what's on our stack. Which is going to be considerably bigger this time. And we will use a frame pointer. Will we? Yep, we're going to use a frame pointer, of course. Okay, I don't know how many. I hope that's enough. It should be enough. Okay, and let's assume that our top of stack is right there. So old top of stack is where the stack pointer R13 is pointing at when we get here. Okay, so our program is ticking along here. First is load register R10 with what is at param2. Param2 is an address in memory somewhere. So it contains some number, parameter 2. We're going to put it into R10. And then we're going to store R10 at stack pointer -4. So stack pointer -4 is the address of this memory location. Okay? So that means param2, that number, not the address, but whatever is at the address, param2, and I'm going to use lowercase to mean the contents of the address param2 uppercase. Okay? That gets stored there. So we push our first parameter onto the stack. Stack pointer now is pointing here because we have write back in that instruction. We're going to load register R10 with the contents of the address param1. So some parameter, call it lowercase param1, gets put into R10, and then we're going to store that at stack pointer -4. So stack pointer -4 means we put it right here. And then because there is write back, stack pointer points there now. Okay, so we push 2 parameters on the stack. Now we are going to branch and link to sub1. Okay, which means down here. Which means the address of the next instruction, 2020, is going to be put automatically into the link register, R14. Okay, that happens automatically by that branch instruction. So we go to sub1, which is where we're branching to. We've got to store multiple fully descending using the stack pointer. Okay, write back, which means as we push these things onto the stack, R13 continually gets updated. So it's always pointing to the last thing that was pushed onto the stack. Again, for the store multiple, we start on the right-hand side. So the first thing that goes onto the stack is the contents of the link register, which is address 2020. So that gets pushed onto the stack. Stack pointer points here. Then we're going to put the contents of the frame pointer, okay, whatever it is. The frame pointer is register 12, right? Register 12 is the frame pointer. So whatever register 12 currently has in it, we're going to push onto the stack. Okay, so the contents of the frame pointer go onto the stack. We'll just call it contents of frame pointer of main, whatever it has in it from the calling program. We don't know what it is, but we're going to save it because we're going to use that register in our subroutine. So we're gonna save its current contents, stack pointer points here, and then we are going to push on the contents of R3, R2, R1, R0. R3, contents of R3, contents of R2, contents of R1, contents of R0. Presumably, we're going to use those registers in our subroutine. So we're going to save their contents on the stack before we overwrite those with new numbers. Okay, and after that, the stack pointer now points there. Okay, so after that, store multiple fully descending at address 2100. That's what's on the stack. Any questions about that? Okay. Okay, now we can go to address 2104, where we're going to add 16 to what's in the stack pointer. The stack pointer currently holds the address of this location. We're going to add 16 to that address. 1, 2, 3, 4, which is this the address of, that gives us the address of this memory location. Okay. Sorry, we're up here. And we're going to put that address into the frame pointer. So now our frame pointer, which is R12, is going to point here to this memory location. This is still our stack pointer because there is no, this is just an immediate operand that is added to the contents of the stack pointer. It doesn't change the contents of the stack pointer. So the address that's in the stack pointer, which is the address of this memory location, gets added to 16, which gives us 1, 2, 3, 4. The address of this memory location, that becomes our effective address where we, and we're going to put that into the frame pointer. Well, it's not an effective address, it's the actual operand. It is an address, but it's the operand that gets put into the frame pointer, right? This plus this goes into the frame pointer. So now our frame pointer, R12, is pointing here, okay? Which means this is obviously the frame for our first subroutine. Okay, and the frame pointer is right there. So now we can access everything in this frame just by using this frame pointer, right? I can either subtract numbers from this frame pointer to give me these addresses, or I can add numbers to what's in this frame pointer to give me these addresses. Okay, so we've got a frame pointer set up. Now we're going to load register R0 with what's at the effective address of the contents of FP plus 8. So FP currently has the address of this memory location in it, and we're going to add 8 to it for 8. Okay? So the effective address is the address of this memory location. So what's at that address, param 1, gets put into R0. Okay? So R0 has our first parameter in it. Notice that the frame pointer does not change. There's no exclamation mark here, no write back. Means FP still pointing here. Next instruction, FP plus 12, 4, 8, 12. So this address, what's there is param 2. That gets put into R1. So now R0 has param 1 in it. R1 has param 2 in it. Okay? Frame pointer is still pointing here. Stack pointer is still pointing here. Dot, dot, dot means something is done with these two numbers and magically we get some result. Okay? We don't care what that is. But apparently the result is stored in R2 because the next instruction that concerns us is to load the contents of R2 at the memory address param 3. So somewhere in memory, we have a memory location that has the address param 3, just like we had an address param 1 and param 2 somewhere in memory. Okay? So we're going to we're going to get another parameter, and we're going to put it into R2, and now we're going to store that parameter at the address SP minus 4. SP minus 4 would be here, so we're going to store what was at the memory location param 3, which is some number, lowercase param 3. Okay, we're on this instruction right here. So we're getting ready to call the next subroutine. by placing a parameter it needs on the stack. And because of the exclamation mark, stack pointer is now here. Okay? Okay, now we're ready to call that second subroutine, branch and link. Okay? So the program counter gets updated, the program counter currently has 2164 in it. That address gets transferred to the link register. That's our return address. When we come back from sub 2, we want to come back to this instruction, to this address, 2164. So 2164 is in the program counter. That goes into the link register, R14. Okay, R14 currently has 2020 in it. We're going to overwrite that 20 in R14 with 2164. That's okay because we've got 2020 saved on the stack. And then we go to sub 2, which is down here. Okay, we're going to put a bunch of stuff on our stack again as we come into the subroutine. We're going to store multiple fully descending using the stack pointer, which is currently pointing here. Okay, we're going to decrement, and then we're going to store the contents of the link register, which is 2164 onto the stack. Okay, so 2164, and the stack pointer gets updated to that address. And then we're going to put the contents of the frame pointer. Well, the frame pointer currently has the address of this location in it. Okay, so we're going to call that frame pointer, contents of frame pointer of sub 1. Whatever the address is of this memory location in memory gets stored in here. Okay, so we are down here. Did I screw up yet? No. So far, so good. And like I said, good thing I'm writing it here. It is in the textbook, though. Okay, so that is frame pointer. Now we're going to store the contents of R1 and R0 on the stack as well. Contents of R1, contents of R0, and we're done with that store instruction. Stack pointer is now here. Again, because of the exclamation mark here. If this exclamation mark wasn't here, all of this would still be put on the stack, but the stack pointer would still be pointing here. Because of the exclamation mark, the stack pointer itself gets updated as we push stuff onto the stack. Okay, so we've done that. Now we're going to add what's currently in stack pointer, which is the address of this location. We're going to add 8 to that for 8, so that gives us the address of this location. We're going to put that into the frame pointer. So now our frame pointer is pointing here, not here anymore. Okay, so now we've built the frame for our second subroutine. Okay. Frame for sub 2. This is our frame for sub 1. Okay, our stack pointer pointing to the top of the stack, frame pointer pointing here. Okay, now we're going to load register R0 with what's at the frame pointer plus 8. The address, the effective address for this load instruction is what's at the frame pointer plus 8. So the frame pointer has the address of this memory location in it. We add 8 to that memory location. For 8 gives us the effective address being the address for this. So what's stored at that effective address, which is our parameter 3, gets loaded into R0. And now we're going to do something presumably with R0, with parameter 3 that's stored in R0 to generate some result, okay, ... whatever that is. Okay, it looks like the result is stored in R1 at the end of that. So now we're going to take and store what's in R1 at frame pointer plus 8. Frame pointer plus 8 is here again. So we're going to overwrite this parameter 3, because we're done with it, we used it already, okay? We're gonna overwrite this parameter with the result of what this thing did here. So let's call that result of sub 2. Yeah. So this gets overwritten with result of sub 2. Okay, and we were using the frame pointer to access that memory location. We could have used the stack pointer to do it as well, but since we have a frame pointer, we use that. Okay, so now we're ready to go back to sub 1. So we're going to return back from sub 2. So we're going to pop a bunch of stuff off the stack. Okay, again using the stack pointer, which is going to pop and then increment by 4. First thing that gets popped off gets put into R0, right? Contents of R0. The next thing that gets popped off gets put into R1. Contents of R1, okay? Next thing that gets popped off goes into the frame pointer. Well, that's going to be this address that's stored here. It's the address of this location in memory. Okay, that's going to go back into the frame pointer. And then the next thing, which is the address 2164, gets put into the program counter. Okay, so now the top of the stack pointer is no longer here, stack pointer is now here. Pardon me, not there, it's here. It's pop, then increment the stack pointer. Okay, so now we're returning from sub number 2. Okay, we've effectively taken off everything from the stack except the result of sub number 2. The CPU is now going to look at what's in the program counter, which is the address 2164. That's where it's going to go, 2164. So now it's going to go back to here, the next instruction after the call to sub 2 inside sub 1. We're going to load register R2 with stack pointer. Okay, stack pointer is here. So register R2 is going to get the result that was created by subroutine 2. Okay, and then the stack pointer gets incremented by 4. So now the stack pointer is pointing here. Okay, the stack pointer is pointing here. We've now totally gotten rid of the stack frame for sub 2. Remember that because the calling program, which was sub 1, put this parameter on the stack, it's the one that takes it off the stack. So now the stack pointer is pointing here. So now presumably it does something with this result that is now sitting in at register R2, and it comes up with some other result which is in R3. So now we're going to store the result of R3 on the stack where the frame pointer is pointing +8. Well, the frame pointer is where now? We updated the frame pointer here. It is now, I never wrote it down. The frame pointer is now here. The frame pointer is now back here. Right, because the frame pointer was restored to here by this instruction here. So we get back here, now we're going to store frame pointer +8, frame pointer +4 +8. So this result from subroutine number 1 is going to be overwritten, is going to overwrite what's there. So we got result of sub 1 is put here. Okay, that's what this instruction is doing. So we've placed the result of this subroutine onto the stack. Now we're going to get ready to go back to the program, or where it was called, which is back up here. So we're going to pop a bunch of stuff off the stack. Okay, stack pointer is still pointing up here. We're going to pop off R0, R1, okay, pardon me, right here. R0, R1, R2, R3. All of these get popped back off and put into registers R0 to R3. Then we're going to take the next thing on the stack, which is right this number here. It's going to go back in the frame pointer. So now the frame pointer will have whatever this is in it, presumably some other address. And then finally, the last thing on the stack, we're going to put into the program counter, which is this address here, 2020. Okay? That's the return address up here. So now the stack pointer is going to be pointing no longer up here. Stack pointer after all of that is going to be pointing here. Because 2020 was the last thing we popped off the stack. So the program counter now tells the CPU, well, go to wherever I'm pointing, which is 2020. Now the CPU goes up here. So the next thing we're going to store what is, up here, 2020. We're going to load register R10 with whatever the stack pointer is pointing to. Stack pointer is pointing to here. It's pointing to the result of sub 1. So we're going to take that result off of the stack and we're going to put it in R10. And we're going to store it at some other memory address called result. Okay, and then finally we're going to put our stack pointer back to the old place before we started all of this by adding 8 to it. It's currently pointing here. 4 plus 8, we're back here to where the stack pointer was pointing when we started. Okay? Tedious, I know, but that's the basics of it. Okay? Any questions about anything we did in there? Wow, I didn't think we'd spend almost all lecture on that, but hopefully it helps to go through it slowly and in detail. Because I expect you to be able to do stuff like this on the midterm, okay? And the only way I know how to do it is to draw it, write it down, keep track of what's in every register. Yes, sir?
On the midterm, how would we show what we're doing or our work for a question like this?
Well, just like I did here.
So would you be able to actually look at that at the end and be like, oh yeah, he knew what he was doing?
Yes, I mean, it's kind of tough to know what's going on here because it's always changing, right? But I mean, I can easily see what you had on the stack if this was your, right? If you drew this, I can see exactly what you had on the stack here, for instance. But I mean, you know, I can't expect you to create a video and show me, well, I went here, and then, like, I mean, that's not practical, like what I did here. Okay, but I could ask you, well, you know, what's on the stack at this point in time, or something like that. All right, we'll see you Friday. This stack, no, it isn't.